Joel has been at SWRI since 1996, so he's been there rather a while, 20 years, or 21 years almost.
I keep track by how old my son is.
I see. Joel is a project manager and science team member for the New Horizons ALICE instrument, and he is also the PI for the Rosetta ALICE instrument. And today he's going to talk to us about the Rosetta mission. Thank you, Joel.
Thank you. So, yes, the Rosetta mission to Comet 67P Churyumov-Gerasimenko. I will call it 67P for short, or just CG. When it's an international mission with accents from all around the world, it gets very interesting sometimes to understand exactly what is going on. So I'm going to talk about the mission and some of the results we had. The mission has ended. And so we're now actually working on the data because we've been so involved in the operations part of it. So the Rosetta is run by the European Space Agency, and it's a 1.3, 1.4 billion euro run-out cost mission. So we're talking real money if you do conversion in whatever year you want. It's an orbiter and a lander with the goal of visiting and studying a comet up close and personal. 11 instrument packages on the orbiter. Some of those packages themselves have multiple instruments, like the Plasma Consortium set of instruments, and 10 on the lander. It's European run, but there are NASA contributions. There are 3 instruments that were NASA contributions. One of them was the ultraviolet spectrograph that I work on. There was a millimeter and a plasma instrument, plus science team members, some software support and things like that. It was very interesting working an international mission in such depth. Without sounding too hyperbolic, I do think this was one of the most challenging missions in history. It was the first comet rendezvous, the first comet landing, the first long-term escort of a comet, all packaged together into one mission. It also had a long lifetime before getting to the primary target. From launch in 2004 to rendezvous in 2014, 10 years before getting to your prime target. There have been long missions, but planning for that long is tricky. Yeah.
Can you remind me just how up close and personal it had gotten before this mission? I vaguely remember some Japanese missions.
So there have been, not to say Rosetta is the first one to get to a comet. There have been others. There was basically the Halley Armada went by Halley, and there was Giotto and others. There was Comet Borrelli. There were others that were flybys by NASA and Japan and Europe, but all of those were fast flybys. And so this is the first time that we were able to rendezvous and get closer to the comet. Those other flybys were thousands, tens of thousands of kilometers, and we were getting kilometers. There haven't been any direct sample return mission from comets, but Stardust flew through and got dust particles from the tail, and we're able to get samples of dust from there and return it in aerogel. We had to have a 2.5-year hibernation again before getting to the prime target. And this is the longest, deepest hibernation for a spacecraft before getting to the prime target. There have been others after the prime mission and their extended missions. But this was an incredibly deep hibernation. Usually you'll have like a beacon telling you every now and then that the spacecraft is healthy. Maybe you can wake up and just test a few things. We literally spun up the spacecraft, never having done a term spin test for 2.5 years, shut down everything except an alarm clock saying wake up on January 20th at 10 o'clock 2014. And we went 2.5 years not knowing if the spacecraft was in fact alive, still working feverishly in hopes that it was. You're success oriented, it's going to work.
Can you say something about why that long-term hibernation was making solar wind measurements?
Sure. I will, and I'll show you in more detail, but it's because to be able to match the orbit of the comet, the comet's orbit goes out just past the orbit of Jupiter. And solar power out there is tough, and there just was not enough once we got past about 3.8 to 4 AU really to run the spacecraft. Just wasn't. So we had to do, solar power at some level out to 4.5 AU. We ran some survival heaters and a few things like that, but for the most part it was shut down. 21 instrument packages, as I said, from separate teams, international teams, everyone with their own goal, that you had to have many WebExes and telecons that worked with Europe time and US time to figure out what you were going to do for operations. A lander and orbiter in one mission, so 2 spacecraft that you had to deal with. Unknown landing environment. So this was done before doing a reconnaissance of the target. And so we had to prepare for an terra incognita, comet incognita, or whatever. We didn't know if it would be a very hard surface, a very dusty surface, a crust over a dusty. So we had to prepare for that, and I'll talk about that in a minute. Changing environment with complex operations. Comets change all the time. It's not like orbiting around some planet that doesn't change very much. Every day, every minute, it can change. And of course, contamination and damage risk. You take your instrument that you built in your clean room to high specs and you put it in the dirtiest part of the solar system, flying in a comet tail. And also orbiting a low gravity body was a challenge that really had not been done before. So just kind of to make sure we have context here in the lay of the land, one of the reasons to go to a comet is to see it in detail, in particular to see the nucleus. This is the engine that really drives the comet. This is on the order of kilometers to a few or maybe tens of kilometers in size. And this is a rocky ice combination that is pretty inert when it's out at the far end of its orbit. And then when it gets into the sun heats it up, the ices sublimate, and you have the cometary activity that drives the things like these tails. But that little nucleus is buried in this mess here. One person's mess is another person's science, but dust tail and ion tail, all of that obscuring the nucleus. So from Earth, with Hubble or what have you, you cannot resolve the nucleus. And so to see what is really driving everything that's going on with these tails, that's then all embedded in this huge coma, millions of kilometers in diameter, you really need to go there. And so that was the goal of Rosetta, was to do that. And comets are important because they come from parts of the solar system that are hard to get to. So instead of sending a spacecraft out to the depths of the solar system, the depths to us, there are 2 source regions primarily for comets. The first is the Kuiper Belt, and this was predicted early on due to the flat orbits of the short period comets. Those comets tended to be in the plane of the solar system, so you expect that the source region for those comets also has a planar geometry. And so this source region outside of the orbit of Neptune was predicted long before it was actually observed by several decades. So the Kuiper Belt, beyond Neptune's orbit, Pluto is a member of the Kuiper Belt. I give it dual citizenship. I still call it a planet, but it's the king of the Kuiper Belt. It's in the disk of the solar system. Many of the objects there were formed in situ. There's solar system dynamics where there was some mixing, but for the most part, these comets, these objects, were held in cold storage for the past 4.5 billion years. So that's why they're interesting to look at. And the name Rosetta, the idea of translating our origins, something old, something ancient, by looking at an example, a comet that could provide us the template for understanding things about the origin of the solar system. The Kuiper Belt's the source of these things that we call Jupiter family comets. Comet 67P is a Jupiter family comet. These objects get perturbed, get pulled into the inner solar system, and Jupiter is the king of the solar system, at least as far as the planets are concerned, and control those orbits. So a lot of these objects have orbits controlled by Jupiter called Jupiter family comets. Eventually, they either get thrown further into the solar system and then break apart or destroyed by too close passes to the sun, or they get ejected. Second source region, there are long period comets or hyperbolic comets that seem to come from a very distant source, and it's isotropic. So by the same analogy, we predict that there's this Oort cloud that is a spherical distribution surrounding our solar system. And you can see by the scale here that it's very large, 50,000 AU spherical distribution. And these are the long period or Halley type comets. So that just gives you the background of the comets and why they're interesting, because they are sampling those outer parts of the solar system that we can't get to easily. So this shows the life cycle of a Jupiter family comet. When it's out by Jupiter, it actually usually is dormant. You don't see activity. It gets closer to the sun. You see the formation of the gas tail and the dust tail. Goes through perihelion and then back out again.
So that workflow, that spherical distribution, is it believed that it is isotropic, or is there some preference playing nevertheless?
So as far as I know, I believe it's mostly isotropic. The way it was probably formed was particles in the disk of the solar system getting scattered out by the giant planets. And they scattered them out pretty much isotropically. Now, there could be distortions to that due to passing stars and things like that. And you can look at the distribution of the comets to try to see if there is some preference. But as far as I know, they've been isotropic. But the question is, how pristine are these comets? We keep saying, they're an example from the formation of the solar system. And they are not truly pristine for a couple reasons. First of all, they have experienced in the Kuiper Belt, if they formed there, collisional disruption in their lifetimes that have done some modification to those. And also the periodic comets, by the time we see them, they've come into the inner solar system. They're already getting thermally processed. So the trick here is to disentangle these effects from the formation environment, the primordial factors. And that gets tricky. And you have to try to look at a number of different ways at a comet. I'll talk about that a little more. Rosetta's science goals at Comet CG are to understand basically the origin of comets, the relationship of cometary and interstellar material and its implications for origin of the solar system. So this is, in the mission proposal, this is what the goal was stated as. To meet those goals, the objectives that we had were characterization of the nucleus, to look at the dynamical properties, morphology, compositions, and things like that, the chemical and isotopic compositions of the comet, the nucleus, and the coma, because that will say a lot, especially the isotope ratios, a lot about origins of the planets in the solar system. Look at the physical properties and interrelation between the nucleus and the coma, and study the development of the comet activity. We want to get to the comet before it becomes really active and watch it turn on. And how does that coma form? Are there certain high activity areas, or is it a general activity around the surface of the comet? So the spacecraft itself, the main Rosetta spacecraft, as you can see here, has a huge wingspan, 32 meters tip to tip, 64 square meters of solar panels. The main Borg cube center part of that is about 2 to 3 meters, and the lander fillet it's about the size of a washing machine, about 1 meter cube. And because we're going to an environment and a target that we've never been to before, we really tricked this out with everything we could do. So we're looking ultraviolet, visible, infrared, millimeter, radio. We have cameras and spectrographs. We have dust detectors, several dust detectors, and a number of other instruments to really look at all the different ways you can at this comet in this new environment. So this shows the instrument deck of the spacecraft. And I'm just going to step through some of the instruments that we have here. So there's ALICE, the ultraviolet spectrometer, which is the instrument I work on. And that's looking mostly at gas in the coma. We have CONSERT, which is a great experiment. It's a radio sounding experiment between the spacecraft and the lander. So when the lander's on one part of the comet, spacecraft on the other, send radio signals back and forth to probe the interior of the comet. COSIMA is a chemical dust analyzer. GIADA is a dust physical properties analyzer, and MIDAS is another dust physical properties analyzer that uses an atomic force microscope. So 3 dust instruments to begin with. MIRO, microwave instrument, measuring the water production among other lines, and thermal properties on the surface of the comet. OSIRIS is our camera, a wide and narrow angle camera. ROSINA is the mass spec, which did an amazing job getting a lot of the zoo of chemicals and species coming off the comet. RPC is the plasma consortium, which contains 5 different packages: a magnetometer, a electron sensor, other high energy particles. RSI, so the radio science investigation, is basically our high gain antenna, but we use that for mass determination, among other things. And VIRTUS, a visible and infrared imaging spectrometer. So that's what we have on the Rosetta spacecraft. And just to pick one randomly out of the collection, the ALICE spectrograph. So this is a shoebox size spectrometer. You can see in the lower picture here, someone holding it. And you have the telescope portion on the bottom here, a primary mirror going through a slit to a grating, and then the detector here. So this has been a really great tool for studying the ultraviolet lines that you see in comets, hydrogen, carbon, oxygen, and looking for other species such as noble gases. The lander itself, I won't go into as much detail on the lander here, but I'll give you kind of the menu of all the different instruments. Again, some more dust instruments, some surface analyzers for thermal properties, for hardness of the surface, cameras, magnetometers, a sample drill with some ovens. So really a fully complex spacecraft itself. And just to answer that question about the orbit and why it took so long there, this just steps through the whole orbit process. So we had launch in March 2004. That was followed by an Earth flyby. We actually had 3 Earth gravitational assists, because this large orbit you see, let's see, where's my mouse? The large orbit that you see out here is the orbit of the comet. So you'll see we're trying to get to match that orbit. And so we had a flyby of Mars that tweaked it a little bit, so we could have flyby of a asteroid. There you see the comet zipping by, our third Earth assist, and now that finally pushes us out into an orbit that starts getting close. One more asteroid flyby for bonus science on the way. And then we had to enter hibernation. And you can see us catching up there to the comet, going through aphelion, and then we finally come out of hibernation, and it woke up. No one woke up dead. Rendezvous maneuver, and then finally in August of 2014, rendezvoused with the comet, and we had 2 months to map and arm wrestle over a landing site because we wanted to land before the comet got really active. So we landed in November 2014. And then the spacecraft continued to orbit and escort the comet through perihelion. And although this animation ends at the nominal end of the mission in the end of 2015, we actually were able to continue the mission all the way out to the limit of where the spacecraft could get power out at about 3.8, 3.9 AU. So that was September of 2016. All of that produced my favorite picture at the time. It's now my second favorite picture. But this is a selfie by Rosetta. And I think at the time it was the first image taken by a spacecraft of itself with a major planetary body in the background, maybe excluding Earth. But I love this with the solar panel going off in the distance and Mars in the background. So let me talk about our target. So Chury, 67P. As I said, this was a Jupiter family comet. The best estimate we could get of the shape, and this shows our best estimate of the shape, was based on light curves. So if you have a non-spherical object, as it rotates, am I losing my mic here? We have the light curve, and as you see that light curve from different aspects through the orbit, you can kind of back out what the shape might be that would generate that light curve. And that was our best estimate of what the shape of the 67P was going to be. That's what we thought we were going to get, and this is what we got. A little bit different. And I have a little model here. I'll let folks hand that around there. This was a big surprise. It was a very pleasant surprise, very exciting. I have to admit, even among the most jaded scientists I knew, when they saw this, they just went, whoa, that's awesome. And, you know, that is the first thing that really catches your eye, is this bilobate shape. This animation was actually made by someone not involved with the Rosetta program, but a Swedish 3D graphics guy named Matthias Malmer, who just took publicly available data and created this model that we all use because it was so well done. But it's a beautiful model, and you can see this is a very interesting object. It's actually very dark. It reflects. It has an albedo. It reflects about 6% to 6 or so percent of light in the visible, and it's about 4 kilometers in diameter. So to scale, I apologize for anyone who works on the Mesa, but that gives you a rough idea of both the darkness and size of the comet. And because of this unique shape, we gave it a nickname. We called it the rubber duck, just because someone came up with it and everyone seemed to like that description. But it's indicative because, you know, there's the small lobe we call the head, then the neck, then the body. And the shape is not completely unprecedented or unusual. We've seen asteroids that have bilobate shape, and some of the flybys that we've had of other comets, Borrelly and Hartley 2, have this bilobed shape. The question is, how did that form? Is it a contact binary, 2 objects that came together? Or is it an object that for some reason, due to non-uniform distribution of volatiles or something else, that created preferential erosion around the neck area, something about its rotation relative to the sun. So the question is, on origins, how did you get there? And we have reasons to believe it is actually a contact binary, two things that stuck together. First is looking at the layering on the two different lobes. The layering on the two lobes of the strata is more consistent with the two lobes having originally been separate than from a single monolithic original body. And so this kind of shows here some of the layers that have been identified and their orientation and the normal of the gravity vectors and things like that. And it's more consistent with it having originally been two separate objects. It would require, to stick together like that, a low velocity, rather gentle collision. Otherwise, it would be disruptive. And you can get those. You can run models of different ideas of parameters of what you might expect for the physical properties of a comet, and you can get things that happen like that with a gentle collision. Now, of course, this is a model run that gave you the answer you wanted. You could also have ones that don't, but it shows the plausibility of being able to do that. And in fact, it is very likely this has happened to that object, 67P, many times already in the past. So first of all, we have comets that are bilobate in shape. So we know that there are other examples as well. There are stress features that are evident on this comet that we've been able to see in detail enough that show that there probably have been stresses consistent with structural degradation. So if you look at this image here, you can see this crack. This is about a 500-meter crack going along the neck, and you can model, making assumptions about density. This is where stresses, as you spin it up, would focus and would create a torsional stress and cracks like this. So again, that holds together with the idea that maybe this is not a once and only thing. And in fact, if you take those models and you spin them up more, if you get a period of about less than 7 hours, it will break apart. But the two objects will not escape from each other and eventually recollide at low velocities into the new orientation. So you can have many breakups over a long period of time.
What's the cause of the spin up?
So I'm glad you asked, because that's what I'm going to answer right here. Because of seasonal effects and the activity of the comet, you can have irregular solar illumination that causes more or less activity and re-radiation on different parts of the comet. So first of all, the shape and seasonal effects drive things like transport of mass from the part that's being currently hit by the sun to the parts that are cold. And the southern hemisphere is pointing towards the sun. It has its summer during perihelion. So the southern hemisphere really erodes a lot. And a lot of that transport goes to the northern hemisphere. So you have a change in the comet properties there as well. And then also the activity, the shape, odd shape, drives the activity. So we have measured the change in the rotation period going from 12 hours, then it slightly increased a little bit, and then it decreased. So we have been able to model where you may have activity and insolation from the sun at different parts in the orbit and get matches to these changes in rotation. So all of these changes are driven by the topology in the orbit. So let me talk a little about the landing. So the Philae lander, this shows the target landing site on the head of the duck, the hemiduck, whatever you want to call it. And so that's where we decided to land that was of interest scientifically and that the flight dynamics people would let us land. You know, some of us wanted to land on the neck, and the flight dynamics people just said, can't do it. We don't think we can do it. So it had to be safe and then scientifically interesting. Luckily, we had many choices we could do. So here is a picture from the lander of the spacecraft after release. It was a free fall. This was not a controlled descent. Controlled by orientation for gyros, but not powered. So this is the lander saying goodbye to the spacecraft, and the spacecraft returned the favor. It was nice to at least see the legs were deployed and things like that. Here is a picture during the descent at a distance of about 3 kilometers or so, coming down on the head. This is now at a height of 40 meters, resolution on the order of centimeters. And we had a 1 kilometer error ellipse on a 4 kilometer size object, which made all of us a little nervous. They hit the intended target site within 10 meters. It was amazing. It was, I just was very impressed. So we hit the landing exactly where we wanted it. And if you look here, these 2 images up here, this is the landing site before and the landing site after. And you can see the disruption here. However, what you don't see is a lander. So the lander had a number of features to keep it on a comet of unknown surface properties. How hard it was going to be, was it dusty or crusty or whatever. So it had ice screws in the feet. It had harpoons. Love flying something that has harpoons. And it had a reverse thruster. Well, the reverse thruster failed to hold it down on the ground because a valve failed. And we knew the valve failed, but we also knew there was nothing we could do about it. The harpoons failed, and we still don't know why. And the ice screws didn't bite in because it didn't have a reverse thruster pushing down on it, and the surface wasn't of a property that they could bite into otherwise. So it's not there. You could see it drifting across the surface to the landing site, but it's not there. But serendipitously, on an image taken soon after, if you look in this corner here and blow it up, you see this little dot here. That is the lander floating across over the surface of the comet. So it bounced. And it actually bounced twice and collided with a cliff once. And this shows the trajectory of the lander there. And it ended up in a very odd orientation with one leg kind of up in the air, kind of wedged in a crevice. These images surrounding it here are images from the pan camera that's on the lander, showing there's some rocks here and what looks like just sky up at top. And this kind of gives a rough idea of how we think it ended up landing. Unfortunately, it was in a shady region, so the batteries could not get recharged. So it ran off the battery power it had to do its first science for about a little more than 2 days. Couldn't recharge the batteries, and that was it. Now, many months later, we did get brief recontacts from the lander, but it obviously had a little regeneration because that place happened to start getting in the sun again, but not enough to start exchanging commands and getting more telemetry other than a I'm awake signal. But, and again, this is amazing, like a month before the end of the mission, we had all given up on ever finding the lander. We tried to image the likely spots and everything like that, but due to a few dedicated people and the camera team willing to use it, we were able to find the lander like a month before the end of the mission. And you can see, you know, it's on this little part of the head here where that red dot is, and looking in this little shadowed crevice there, we really had to stretch the image, and there's the lander. And it was just a nice closure, if nothing else. It wasn't doing any more science, but at least we knew it was there. But it was also useful for that radio sounding experiment to pin down the location so they really knew exactly what the path of the radio waves were through the nucleus. But the bounce gave us some bonus science. The lander started doing its science as soon as it did that first contact. And the magnetometer on the lander was recording to look for any intrinsic magnetic field. And at the same time, the spacecraft was recording 17 kilometers away the magnetic field. And they did comparisons between the spacecraft and the lander as the lander drifted over to see if they could see any changes in the lander measured magnetic field relative to the spacecraft. And within the uncertainty of the measurements, they did not detect a magnetic field. So all the field variations they saw were consistent with what they saw at the spacecraft. And so they were able to put limits on that. Intrinsic magnetic field magnitudes less than 2 nanotesla at the cometary surface. And why this is important is if in the formation of the solar system, you think that the early magnetic field in the solar system was a significant factor in the formation, and maybe there was some locking in of the magnetic field early on, you might still see that in some of these remnants. And they were able to put a limit on that. There was no significant magnetic alignment in the protoplanetary nebula on the scale of meter-sized objects. So that's an interesting result to go back to the people who do solar system formation. The nucleus is just amazing. It's dusty in some parts. It's very consolidated in other parts. You see areas here that look like a lot of mass wasting. All these things here that look like impact craters are not. All of these circular or polygonal shaped regions are due to either surface collapse or some type of mass wasting that goes on. There are only a couple things that we think might actually be craters. Part of that is the surface of the comet is relatively young. It loses a lot of surface and a lot of fresh dusting. But you can see mass wasting at the bottom of cliffs there. You also see pits. You see pits with small, few or meter-sized scale. And the question is, are these actually the scale size of the building blocks of objects in the solar system that built things like this comet? They could also be made by certain types of sublimation, so it's not a closed case. But these pits are also an area where you see activity. You can see some gas coming out of this pit here. So there are fresh exposed ices there. However, if we look like with our the ALICE spectrograph, and we look for, if you look at this blue line here, this is a model of water ice. And the histogrammed data are the UV spectrograph that we had to really bin for signal to noise for the case of this observation. It should drop down precipitously if there was water ice on the surface. We don't see it, but it looks like there's a good match with some organics on the surface. And in fact, you can see here our reflectance. In the UV, it reflects 2% of the light. It's incredibly dark in the UV. We could make it things that dark. With possibly an upturn there. And if you use models, that could be an upturn of an organic feature if we were able to go out to longer wavelengths. The lander was able to test the hardness of the surface and thermal properties with a hammer called MUPUS, which was put out on an arm and basically tried to hammer itself into the surface. And it tried and it tried and it tried, and it actually, other than the top few centimeters, it was not able to penetrate the surface, and eventually gave up and even fell over. So they found that there was resistance to ground penetration on the order of more than 4 megapascals. They were able to measure diurnal surface temperature variations of 90 to 130 degrees Kelvin. And they think there was an initial layer of dust that the hammer was able to go through, but then it hit something really hard. Probably just very, very hard ice, which is very hard at those cold temperatures. This list of physical properties, I just wanted to point out 2 of the points. One is the bulk density, which is on the order of half that of water ice. And that, with the total mass and volume and everything, gives us a porosity, a overall porosity of 70% or so. So this is a very porous object. You can imagine many small things slowly coming together into a very porous structure, and then creating a hard, crunchy surface over that through passes by the sun and sublimation and dust sintering and creating a surface over that. But not just ALICE, but other instruments did not see any significant ice on the surface. There were small ice lines in some of the detections, but mostly it was ice-free. The coma, something else that we looked at here, and you can see this wide range of activity going on in the coma. One of the main things we were going there to look at, this was with the Rosetta mass spec, is the deuterium to hydrogen ratio, and how that matches to, say, the Earth standard deuterium to ice ratio in water. Were comets a primary source of Earth water? That's one way to get a handle on it. And so you can see here the Earth value compared to a number of other things, such as some meteorites, although those tend to be very dry. So the question is, could you get enough of those to bring water to Earth? But at least they have the right number for D to H ratio. These Oort cloud long period comets are all too high. There has been one upper limit and one measurement in a Jupiter family comet. So the question is, does this Jupiter family comet have a D to H ratio that also is consistent with Earth or not? And drum roll, no, it is much higher than Earth. This is interesting for a couple reasons. First of all, it means perhaps comets were not the main source for water. Pardon me while I take a drink. Although they have hit the Earth, so every bottle of water does have comet water in it, guaranteed. But maybe not the primary source. But also it means that this class of comets that we've been calling Jupiter family comets may actually have come from different sources within the solar system that got mixed a little bit into this one dynamical class. So that's an interesting result in itself. Rosetta was also able to measure, in addition to the D to H ratio, the argon ratios, which were compatible with Earth. The argon to water ratio, however, was higher by factors of hundreds more than the Earth value. And the nitrogen seems to be depleted relative to CO significantly, although nitrogen could have been lost preferentially, so it could be a fractionation issue. It's not completely clear. But the main point of this is that these and other measurements, discovery of molecular oxygen and other things, point to the origin in the Kuiper Belt with temperatures on the order of 30 degrees Kelvin, and that these Jupiter family comets probably were not the source of water, argon, and nitrogen on Earth. And then one of the last things I want to talk about here are just outbursts, because the question was, does a lot of the activity happen in focused areas during short periods of times or globally? You saw in that montage, there was a lot of global activity, a lot of gas and dust coming off from all over. But there are also these very focused outbursts. These 3 images were taken each 18 minutes apart, 18-minute separation. This was a very short and very collimated outburst. And here's another series of images. This is over a 12-hour rotation period. And you can see that outburst right there during just one image. So we have these outbursts that happen. And the question is, how do you get outbursts? How does that happen? We see two different types of outbursts. We see dusty outbursts, and this is the ultraviolet spectrum. And you can see before the outburst, this lower spectrum here. And then after the outburst, the long wavelength is highly elevated, reflected sunlight off dust. So this is very dusty, but the ratio of the emission lines does not change significantly. Conversely, we see gassy outbursts, where the ratios of the emission lines change significantly, but we see no evidence of dust. And so that is telling us something, that there are a couple different types of outbursts. And at least one way you can get an outburst is if you have a hard layer and a cavity with an enhanced collection of ices, and the thermal pulse goes through and hits that area of ice, heats it up and sublimates, increases the pressure enough to then break the surface and have an outburst. Yeah.
Is that the origin of those photons in the UV spectrum? Are those all just scattered light from the solar chromosphere, or what is that?
So most of these lines you see here are cometary lines. Some are solar lines. We try to clean out those annoying solar lines by getting some solar spectrum around the same time. So what you're seeing here are emission lines of species in the coma of the comet.
Those photons originate from inelastic collisions within the coma itself?
So this
is not photons scattering from the sun?
No, this is not photons scattering from the sun. Let me say you have fluorescence of many of these lines, but let me go into a little more detail here, specifically looking at the oxygen lines. The oxygen 1356. In fact, let me pull up this here. If you look at the forbidden or semi-oxygen 1356 line, that is much higher than it should be due to fluorescence alone. So this is probably due to electron disassociation of CO2, O2. And this has not been seen before in comets because the scale we're looking at here is kilometers and tens of kilometers in the inner coma. But from the Earth, you're looking at tens of thousands to hundreds of thousands of kilometers, where that scale, you don't see it. The outbursts also change the relative abundances of some of the chemicals. And also, very interestingly here, if you look at the magnetic field, it created a diamagnetic cavity around the comet. We were flying outside of that diamagnetic cavity. The outburst happened, and the cavity appeared to expand to encompass the spacecraft, and the magnetic field just plummeted. And also, when is an outburst not an outburst? So here we see a time scale, a time evolution of some of the lines we look at, the oxygen lines, the hydrogen Lyman beta line, and carbon line. And you can see them have this sudden increase. That's signature of an outburst. However, due to a very enterprising undergraduate who kept up with the literature better than some of us, he read that the Plasma Consortium folks detected a coronal mass ejection hitting the comet at the same time. So what we actually have here is not an outburst that the lines didn't change due to the intrinsic increase in electrons and species from the comet, but due to the interaction from the CME hitting the comet, perhaps increasing electron densities by compressing it a little bit. So this is the first time we have seen this effect of a CME on a comet. We've seen tail disconnections before, comets and things like that, but we haven't seen it light up and light up from the inside. So suddenly this was a new thing. It's like, oh, we should go back and look at all our previous outbursts and see which of them correlate with CMEs. So we're doing that now. And let me just finish with dust, because dust, we had 3 instruments looking at dust. Giada was looking at found 2 different kinds of dust. These fluffy aggregates that seem to be very fractal in shape, and these compact particles that seem 2 very distinct classes. And the compact ones seem to correlate with active areas, outbursts, and follow solar illumination. Whereas the fluffy ones seem to be more generally distributed. Like maybe they come from the more gentle, general activity that goes on around the comet, but you can only either loft the more compact ones or something else about the process of outbursts that are more conducive to compact particles. MIDAS, which is the atomic force microscope, also found basically consistent 2 class of particles, larger and smaller, and also found that these tended to be very fragile aggregates. In fact, fragile enough that the tip of the microscope would often break them. Then you'd have Comet stuck on your tip, but luckily they have several tips, so they could get a clean one. Spacecraft charging probably had a lot to do with the dust and what dust we got. It probably biased us from getting some types of dust because of spacecraft charging. And here are just some pictures of some of the dust taken by COSIMA. You can see some kind of stayed together. Some look like they kind of broke up on impact into smaller pieces. And this dust was great. It tells us a lot about the comet, but it also makes it hard to fly around the comet because you're flying through all this dust. And you have star trackers trying to track the orientation of the spacecraft using, stars it can see. And if you have dust confusing that, you can have a lot of false detections by the star trackers. So this forced us, as the activity of the comet got bigger, and we really wanted to see more in detail, we had to fly further away because the activity was forcing us to do so for safety of the spacecraft. And this is just an example. This is slightly forward scattering. You can see this little diagram here. Here's the spacecraft, and here's the sun, and dust particles coming off. And you can see a few dust particles kind of going through there. Now I'm going to turn the spacecraft around and look at backscattering. There are 7 guide stars in this field. You can see why our star trackers failed, and the spacecraft goes into safe mode. So we have to fly far enough away to avoid that problem. And it's not only dust, but I don't know if you want to call it big dust, but you have large chunks. So you have to be careful of spacecraft safety there. So we had our final descent. End of mission. The decision was to bring the spacecraft down as close to the comet as possible. Basically impact the comet. We could have flown it off, but it wouldn't have survived for another round. We might as well get the best science we can at the very end. So as you can see, we did a few orbits, then did this death plunge right onto the comet. And that ended up with, I'm going to show one result from ALICE, from our spectrograph. This plot here shows the spectra we got within distances of few hundred meters of the surface. Resolution on this was just meters in scale. And it looked the same as the large scale comet. In other words, when we got closer, we did not see small ice patches that finally resolved out or something like that. It was amazingly uniform in the UV at all scales. And then this, of course, is the final from the camera, a little out of focus because you're so close. This was taken about 20 meters above the surface. It's the last image taken. You can see the scale there of the image, 1 meter. The resolution per pixel is millimeters. And that was the end of the mission. So rather than finishing with the conclusion slide, and because like I said, we're still working on the data. There's still a lot more. I'm not going to say there are any conclusions yet. We have lots of interesting results. But I wanted to end instead with what is now my favorite picture. And this is another selfie of the spacecraft with the comet hanging in the sky overhead and even a little jet coming out of it. And I have to admit, this was working decades on this mission. This was the first time that it really hit me in the gut that I actually felt like, wow, I was a part of this, you know? I actually touched that spacecraft, and then there it is. And especially for, you know, a group like this, people who we do research, we may be spending all our time debugging our programs or, you know, reducing data, and every now and then you write a paper that has a nice result, but especially also in looking on missions too, just taking a step back and realizing what you have actually accomplished. You know, even beyond that cool result in the paper, something that tells us something more about the solar system or the universe we live in. And that this spacecraft that we build is visiting a 4 billion year old ancestor from the formation of the solar system is really amazing. You know, it's something to write in your annual letter to friends from high school, you know? So I just wanted to leave with that, just to remind all scientists, remember the big picture and how cool it is what you do. And with that, I'll take questions. Thank you. Yeah.
Ricky.
Did the spacecraft stay on the comet, or did it bounce off?
We don't know. So there are some you can ask people what they think happened. So the lander bounced, but different instrument didn't have these big solar panels to you know, absorb the impact and everything like that. The spacecraft was programmed to shut off on impact. And there was a lot of discussion about this. The engineers said that due to International Frequency Union rules, you had to make sure the spacecraft was dead, and not going to interfere on that band any other time for any other mission. I don't buy it. You know, the more cynical people said they wanted to make sure the spacecraft was dead so that you wouldn't spend any more funds trying to hear for the signal again and people wanting to do some more. And the thing, the thing is, though, as soon as impact happened, the high gain antenna off point anyway, and you wouldn't get any more information. It'd be very unlikely that you'd get any more. So we never got any information post impact.
What about if you model the velocity vector and the surface?
So those who have done that modeling think that it probably did not have a big bounce. It probably pretty much stayed where it was. The solar panels absorbed a lot of that, and it wasn't designed to land, so there was all sorts of compression and loss that way. So it probably stayed where it is, unless, you know, due to an outburst or something, nudges it off, you know, and it moves somewhere else. Yeah.
I have two questions and then an additional remark. First question is, I mean, what is remarkable about D over H is that the weight ratio of these two isotopes is the biggest of all isotopes. So when you observe an object where deuterium is in excess as compared to Earth, what argument do you have that you maybe not are looking at a selective loss of the lighter element, and you had originally an object that indeed had a lot more
So I have to defer to those who did the modeling to say that those on the Rosetta project who did the modeling looked at fractionation issues to see if that could have had an effect on the D/H ratio. And they say, according to their modeling, making whatever assumptions you need to make about the protoplanetary nebula and temperatures that the comet has gone through over time, they think that that cannot explain this difference.
Second question is about the magnetic field. With this obvious reconfiguration of this object, how can you have confidence that you can keep a magnetic field over 4 billion years?
So if you think that, although you've had reconfiguration, if the lobes themselves were the primary original objects, so you may have had objects on the scale of that size connecting and then maybe breaking apart and reconfiguring, at least on the scale of the lobe, so a kilometer or so, those may be more primordial elements. The measurements that they did, especially with the lander that close to the surface, shows that even at that close scale, they don't measure magnetic field. So you could have had collisions that heated things up, and you could have lost some primordial magnetic field. And these are just, the lobes themselves are reconfigured rubble piles from collisions where you've now lost a preferential orientation. So that's an assumption you can make, but as far as we've been able to see, the lobes themselves don't seem to have been reprocessed rubble piles.
Do you have any idea of like a decay time?
No,
Primordial field in there?
I don't. And you said you had one comment.
Yeah, the comment I wanted to make is that we all know that the mission was delayed because of the original launch not happening because of the delay of the Ariane 5.
Right.
And then you had to go for a different comet. The tragedy in that was that one of the designers of the lander, his name was Rosenbauer, didn't live to see his lander form. And Harry had the greatest respect for him as an instrument builder and as an educator of the people working on space instrumentation. And I thought I should mention this name.
And I think, that's the bittersweet part of these very long missions. We had many people who died over the course of the mission who were the movers and shakers to get the mission to happen or to build instruments. It was very sad that a number of those people weren't there to see the arrival at the target and their handiwork. We've tried to acknowledge them in naming of some features on the comets. Actually, the IAU allows us to name features on comets however we want because they're not permanent features. So we don't have to go through the arm wrestling like we have with Pluto. So that's great. But I've had undergrads working on this who weren't born when the mission was born,
You were talking about hard ice beneath the solar layer, I think you said. And was that actually water ice? Or do you not know?
We don't know. We can look at the gas coming out and make inferences about the sublayer ice. It's almost certainly water, CO2 ice. Water ice is very strong at cold temperatures.
Oh, I have a really dumb question. Okay, so so how old is a typical water molecule in the Earth's ocean? Is that relevant at all to this question of comparing D-to-age ratios?
It's not a dumb, well, if it's a dumb question, I don't have an answer for it. I have no idea. I have no idea. That's a good question. I don't know if anyone here knows.
Is it possible to say anything at all?
Well, oh, you mean as far as just looking at the, well, you can look at the D to H ratio a number of different ways. Yeah, I don't know what the impact is of, lifetime of a typical water molecule as far as that's concerned.
They've been around for the entire Earth's history, or
I don't know.
Okay.
Developed dissociation even on Titan, right?
I mean,
It's really surprising.
there must be. And if you still think the D to H ratios should still be relatively indicative, regardless of whether they're long-lived or there's a lot of cycling, unless there's some preferential reconstituting, basically.
Yeah, the deuterium in Earth relative to hydrogen has changed as the vapor form. As the hydrogen got boiled off the Earth,
Yeah.
evaporated. I don't know.
Yeah.
All right. Well, thanks, Joel, again. Before we go, I just want to mention two things. First, Joel also hosts a science radio show on KGNU on Tuesday mornings. So if you want to hear more about this kind of stuff, you can tune in there probably and hear him talk about all kinds of stuff.
Maybe I'll grab some of you if you have anything you want to talk about sometime. I'm not always the host on Tuesday mornings. We cycle through.
More data do you have to analyze?
How much more data? We have more data analyzed than we've analyzed. That's the best way I can put it. ALICE alone, we have over 70,000 spectra. And we've probably published based on a few hundred.
All right, last comment is that we will not have a colloquium next week. We were unable to find a speaker. So if you have suggestions for speakers, please come talk to me just come talk to me about it and we'll get somebody on the schedule. But instead of the colloquium next week, we will have a solar focus series hosted at NSO. Axel is organizing this, and Phil will be leading a discussion on the chromosphere. See you guys in 2 weeks here. Bye.
Thank you.